So before I give you some questions or we discuss something, I want to ask you: anybody of you has any doubt in any part of the topics which are coming in the UT? Any topic, any doubt? Functions, files, stack, anywhere? Good. Nobody has any doubt? Good. That's nice. How many of you are there today? I want to see that. Will there be patterns? Patterns, Pranav, like how? What kind of patterns? Yeah, not in this exam, but not in this exam, you will not have. Okay, so you're very familiar with all the kind of files, you're familiar with the working of the stack, you're familiar with the working of the functions. So we'll go on. So I'm thinking of now going on to the next topic itself, which although is not part of your UT, but is the next topic that we have to do. Is it okay if we go on the next topic, or would you still want to revise the questions for your UT? Do you want me to give one or more questions for your practice test for your UT, or do you want me to go on the next topic? Because now that if you say that you've understood everything, then you need to move on also. Tell me, beta, all of you are here. Whatever you all say, we'll go by that. You want a revision, we'll do a revision. You want to go ahead, we'll go ahead. Revise, okay. Right, let's revise. Okay, so let's revise through certain questions which have been coming in the board exam also, and which typically also you may get. So let's start with functions. One question of function, one of files, and one of stack. If we are able to do in this time limit, let's just do that. So let us say in terms of, let me give you a question and then discuss on that part. How many of you remember binary search? We've done binary search. How many of you remember that? So Pranav and Sarthak, if you're raising hands, you can just tell me, either speak up or write in the chat box. Beta, what are you trying to say? And meanwhile, tell me binary search. How many of you remember what is a binary search, or what is a search for that matter? Linear search and binary search. You remember? What's a linear search? What's a binary search? Nobody remembers. Yes. Certain elements in a list of elements. Absolutely. So when we have a list, so let me just put on the ideally and share the screen, and then we'll discuss it simultaneously. Let me share the screen. Okay, so before I share the screen, let's say you have this list: one, two, three, four, five, six. So I want you to look at the chat box because I'll first discuss before I do it. So supposing you have this list of six elements: one, two, three, four, five, six. Now, if I have to search for an element in the list, let us say I want to search whether two is present in this list or not. This is a list which I know. You may not know the list because the user has entered it. So if you want to search for an element in the list, basically you traverse the list, you check each element, and if the element is matching what you're trying to search, you say it is found, else you say it is not found. So like Pushkar says, you start traversing the list for I in L, and then it is if this I is matching what you're trying to search. So then you say it is found, else you say not found. So now this is a kind of a search which is called as a linear search, where you start from the beginning, traverse till the end, compare each element, and try to figure out whether it is there or not. Now, in a linear search, the best case scenario is that the element that you are searching for is the first element. So, for example, when I take this list, suppose I'm searching for one, and one is present in the first position itself. That is the best case scenario. Best case scenario means which takes the least amount of time and effort. So in the first comparison itself, I will come to know that the element is there in the list. So that is my best case. My worst case scenario would be, what would be the worst case scenario in this case? If the element is, okay. So the worst case scenario is either the element is last element or does not exist in the list at all. Which means if there are, for example, in this case, there are 6 elements, right? So that means minimum of 6 comparisons I need to find out whether the element is not. So if I'm searching for 6, it will search the first element, second, third, fourth, fifth, and sixth. Once it reaches sixth, if that is the last element, it tells me it's the last element. If it is again not the element I'm trying to search for and you've reached the last of the list, it will say it is not present in the list. So the worst case is that the element that you're searching for is the last element or is not present in the list. In either of the cases, it will have to do the comparison of all the elements in the list. So if there are 100 elements, it will do 100 comparisons till it reaches the end. So that is your worst case scenario. Obviously, your average case scenario is somewhere between your best case scenario and the worst case scenario. So that would be approximately the half the number of comparisons on the list. That is your average case scenario, which is here. In case of a binary search, what happens is, number one, the main difference is that in a binary search, the prerequisite is the list must be pre-sorted. It should either be in an ascending order or a descending order. So in a linear search, there is no requirement of sorted list. It does not matter whether the list is sorted or not. But in a binary search, it is a prerequisite that the list be sorted. And how does the binary search work? The binary search works with the fact that you have to you divide the list into two, search the first half, search the second half. So let's take the same list 1, 2, 3, 4, 5, 6. And the same list, now this mandatory, it has to be pre-sorted, either ascending or descending order. What we basically have to do is you have to divide the list in half, check out whether the element you're searching for is, where is it placed with respect to the middle element. Okay. Now suppose I'm searching for element 2. 2 would be in the first half of the list because it is a pre-sorted list. So you have to consecutively go down the list, down the list, down the list till you reach the element you're searching for or the list itself is exhausted. So let's take an example. Yeah. Let us say my list is, let's take a pre-sorted list 11, 22, 33, 44, 55. Okay. Now assume this is the list. The first thing I have to do is find out the middle element. Middle element, how do I find out the middle element? Which is the middle element of any list? How do I find the middle element of any list? Absolutely, length by 2. So I try to find the length of the list for which I have a function with me, length function. I divide it by 2 to get the middle of the list. So in this case, the length is 5. If I do 5 divide by 2, I get 2.5. 2.5 is not any index. Index is supposed to be a whole number. That's why he's written as double division operator, which leads to the integer division. So in this list, you will get the midpoint as 5 by 2, which will give you 2. So the whatever element is at index 2 is your middle element. Index 2 right now is 33. So 33 is the middle element. Once we found the middle element, now which is the element we are searching for? Let's say I'm searching for 22. Okay. Now since it's a pre-sorted, you have to keep in mind always it's pre-sorted. Now since mid is 33, I am searching for 22. Obviously it cannot be after 33, it has to be before 33. So somehow I have to absolutely reduce my list to something like this. Forget about 44, 45, because definitely 22 is not going to be on that side of the list. It has to be on this side. Now, again, I have a shorter list with me. Again, I try to find the mid of the list. The mid of the list becomes 1, which means 22 is the element at the middle of the list. I am also trying to search for 22. So I get it. I said, okay, yeah, the element matches and I'm able to find it. Supposing I was searching for 10, what would have happened? I would have not found it here, but I know it's on the left side. So my list would further reduce to this. When I again try to find the mid would be 2, which is 1. We again come back to 22. So the mid again becomes 22. Again, I'm trying to search for the element in the mid. 10 is again less than 22. So again, the list will reduce. Now, this will become a never ending process, right? This will keep on happening because every time there is a list of 2 elements, the mid has come out to be 1, my element does not match. How do I do about it? Which means I have to have one more condition apart from the fact that if mid is not matching my search, I have to have one more condition to tell me when to stop. Otherwise, this will become a never ending process. And here comes into play two more variables which are called as low and high. Okay. So in the beginning, right at the beginning, when we had this initial list, which was this, now I'm introducing apart from mid. So here, let us say low was 0, high was length of the list by 2, or rather length of the list minus 1 would be, and mid would be, as we said, length of the list by 2. Okay. Why I require this low and high is because I need a condition where my search is going to end. Now, if you see, low is always less than high. The typical condition when we encountered last time here, right? This was low, high, and this. So what was the value of low? Low was 0 in this case. High was length of the list minus 1, which was 4. And mid was this was the first case. In the second case, when my list is reduced, if you see, when I was searching for 22, this was my reduced list. In this list, low still remained 0. High became length of the list minus 1, which is 2. Mid became 3 by 2, which was 1. Okay. Further scenario, when I reduced to further 11, 12, low became 0. High became the length of the list minus 1, which is 1. And mid became I can't go any further. I have to stop because here your list you've traversed, you've not been able to find the middle element, or the mid element does not match your search, but there is nothing else to do. So therefore, we need to come to a conclusion as to our stop condition. What will happen when you do not find the element of the list? Okay. So I'm going to write the program for it, and you can see that. What I want to do before the program is, in this case, the best case scenario is where the element is the mid element. Element is mid element. That is the best case scenario. Worst case scenario is the element does not exist at all. So you've done n number of comparisons, but the element does not exist. My only question to you is, if this was the list 11, 22, 33, 44, 55, and you were searching for 44, how many comparisons would you have made in a linear search, and how many comparisons would you have made in a binary search? Tell me. If your search element was 44, how many comparisons would linear search require? How many comparisons would binary search require? Yes. Your linear search would require 4 comparisons. So it will compare 11 equal to 44, no, 22 equal to 44, no, 33 equal to 44, no, 44 equal to 44, yes. So 4 comparisons required to check whether 44 is in the list or not. Whereas in a binary search, you would have divided into half. So the first comparison is with the middle element, 33. You know it's not 33, is not 44. You would have gone on the right side with your list as 33, 44, 55. The next mid element would be 44, and you're comparing with 44, and you found 44. Effectively, 2 comparisons. Okay. And this, please remember, we are talking in a very short scale. We are talking of just 5 elements. Imagine if there are in the list thousands and thousands of elements. Look at the number of comparisons which will they will increase exponentially. So what happens is, in a smaller list, we say linear search is effective because you're simply traversing and you're not doing the calculation for the mid, high, low, etc. You're saving on that time of comparisons, on that type of calculations rather, not comparisons. So for a smaller list, linear search becomes more effective. Because if you don't do linear search, you first have to do a sorting of the list, then do the calculations of the high, mid, and low, and then do the comparisons. In a bigger list, it is always better to do binary search because, of course, you have to pre sort the list. Of course, you have to do the calculations for low, mid, and high, but the number of comparisons drastically reduces. So it's a faster search when you have a larger number of elements. And just to bring to a perspective, Not that you should be doing it, but there are other types of searches also. We are concentrating only on linear and binary search, so at least you get some idea as to there are multiple type of searches, each has its own advantages and disadvantages. Okay, so coming back to binary search, now in a binary search, you see, you are finding the mid again and again. When anything needs to be done again and again, it needs to be put in a loop. So when we start writing the code for a binary search, we have to see that every time we are searching the mid, every time we are comparing, which means um, these two operations should come inside a loop because it's happening again and again. But if it is inside a loop, it also means that you need to stop the loop at some point of time. Just wait, Peter. I'm just putting you on mute for a second. Yes. So we were talking about the fact that in a binary search, the number of comparisons is very few as compared to in a linear search. But it is not very effective for smaller lists because in a smaller list, then the overhead increases. Okay. So now please tell me, can somebody write only that part of the code? It may not be the exact code, but what do you think should come in the for loop? Like I said, the calculation of mid and the comparison. So what exactly should come there? Can somebody just write that part? Maybe not the whole thing, just that part. Yeah, the part where you need to find the mid and do the comparison, that should come inside the for loop. So what should be the condition of the for loop and what you should write within the for loop? For example, for something something, this mid calculation, mid is equal to some calculation of mid in any format that you want, something like this. And within that, the comparison also, if your mid matches the search element, what should you write? So please write the loop part of it, somebody. You may use another loop if you want. If you don't want to use the for loop, you can use any other loop also if you want. But what should come with inside that? While x not equal to value, okay. For x in list, mid is equal to low plus high by 2. Yes. If mid equal to x. Okay. If mid equal to x, then what? What happens if mid equal to x? Then what? And vice versa, if it is not, then what? Okay, I'm pasting a code here. I want you to have a look at it. So you have a list and you have a search element. You have the low, high, and mid. So in the beginning, they are just initialized, okay? Because initializations are required when we use it. Now the condition is while low is less than equal to high, you calculating the mid. Why this condition is, we'll just discuss it. You get the mid, you check for your search element. If it is less than the mid, you have to go on the left side. If it is greater than the mid, you go on the right side, else you return the middle element itself. Okay. So if you look at this code carefully, what is happening is the changes are happening in the low and the high. So if it is in the low, which is on the left side, then the low does not change, the high changes. It becomes mid minus one. Why not mid and why mid minus one? Because you've already checked the middle element. So to reduce the number of comparisons, it becomes mid minus one. If your search element is greater than mid, the high will not change, the low will change to mid plus one because right hand side of the list. So either it is on the left side, either it is on the right side, or it is equal to the middle element itself. Okay. So that is why the code says either it's on the left, you check the left, or on the right. If not, then you return the mid. And at the end of the whole thing, you return minus one if the element is not found in the list. Now, because we are changing the low, the high and the low to mid plus one and minus one, eventually we'll reach a case where your high will become equal to low, or high will become greater than low. When this case is reached, that is the point which tells you that the list has been exhausted, the entire list has been checked, nothing has been, the element has not been found, and therefore implies that the element is not present in the list. Okay. Please take a minute to read this code. You want to copy it, copy it. This is just the definition of the function. Of course, you have to call the function and provide the relevant parameters to the function. But just have a look at this function, go through it, and see whether it makes sense to you. In the beginning, low is always 0. High is always the length of the list minus 1. You have to start the calculations of the mid, which you have put inside a loop, and then start comparisons with the mid position. Okay. Now remember, you have to go on the left or the right side from the mid position, and that's how that whole loop is working. Unless either you have either found the element or reached a place where you can confirmly say the element is not existing in the list. And how can you say it confirmly? At a position where your high becomes less than equal to, greater than equal to low. Okay. At this is the position where you can concretely say that the element no longer, we've checked the entire list, the list is exhausted, and the element has still not been found in that list. Okay. So please copy this, try this, try to understand this, run it in your IDLE. Find out if you were getting any errors in the code or is it running okay, and see step by step if you're not understanding anything in this. Okay. So your exams have been rescheduled, you've got the revised date sheet also, and if things go as usual, then you'll have the tests in the revised date sheet, as per the revised date sheet. Okay. So if there's any doubt, Peter, you can just let me know. Otherwise, I will end the session now. So I'm ending the session. If you still have doubts, please WhatsApp me separately or in the group, and I'll be able to answer your questions. Okay. Thank you so much. I'm ending the class.